Hi everybody. Today, in our episode, we will see equilibrium equations and Le Chatelier's principle. Equilibrium reactions, as I've said in the acid-base video, use this symbol. It means that this reaction can go forward, meaning that in our case calcium carbonate can turn into calcium oxide and carbon dioxide, but it's also reversible. So the calcium oxide and carbon dioxide can come back together and form calcium carbonate. Now that we know what an equilibrium expression is, let's see Le Chatelier's principle and factors that affect equilibrium. So when a reaction is at equilibrium, it means that the rate where the reactants become the products and the products become the reactants are the same. So rate of calcium carbonate to calcium oxide plus carbon dioxide must be equal to that of the rate of calcium oxide plus carbon dioxide becoming calcium carbonate. This is equilibrium. When it's not equal, it is no longer in equilibrium. Right now, the reaction rates are the same. But what if we add more carbon dioxide gas? Pause the video and think about it for a little while if you want. Now, because there are more carbon dioxide, there'd be more carbon dioxide pushing down on the surface of something. Because carbon dioxide wants its pressures constant, it's going to try to become more calcium carbonate and bond in with more calcium oxide. Now until it hits equilibrium, it's going to try and go into calcium carbonate. So let's just say it went back to equilibrium. Now, what if we take away some of the calcium carbonate? Well, turns out calcium carbonate is a solid. And if you remove some of a solid, it wouldn't actually affect equilibrium. So it's still at equilibrium. But what if we move all of the calcium carbonate? So the amount of calcium carbonate down to 0. Now things are going to change. Because there are no more reactants, but the products are still going back to the reactants, the reaction will highly shift to the calcium carbonate side, or the reactants. But how about increasing the volume of the reaction vessel? If we increase the volume, there'd be less average density of carbon dioxide, meaning that there'd be less carbon dioxide for a certain volume. But carbon dioxide, like any other gas, wants its density constant. So this time though, it's gonna shift to the carbon dioxide and calcium oxide side. So this would be bigger than this until it's gonna come back to equilibrium. Now let's see a harder example that involves heat. This equation is a dissociation of ammonium bisulfide becoming ammonia gas and hydrogen sulfide gas. Now don't open this bottle. Just don't. The smell will kill you. Okay, so now this is an endothermic reaction, meaning that the ammonium bisulfide will dissociate, taking a little heat energy with it. So it's going to decrease the temperature. But to make the temperature constant, ammonia and hydrogen sulfide will recombine, forming more heat. But what if I drop the temperature? So if it's like this, at room temperature, what if I drop the temperature to say about 0 degrees Celsius? Pause the video and think about it. Now, decreasing the temperature is none different from decreasing the heat. So it's decreasing one of the reactants. So the products will go ahead and make more of the reactants until the temperature goes back to room temperature. How about increasing the heat? Say like to 50 degrees. That's hot. Now, this time we're increasing reactants. When ammonia and hydrogen sulfide combine, it's going to create heat. So this time the endothermic side will take over, forming more ammonia and hydrogen sulfide until the temperature goes back down to room temperature. Now, let's see an even more complicated equilibrium with 3 sides instead of the 2. Here, I actually wrote the equation that happens in our blood, the buffer system. The equilibrium reaction that keeps our pH constant at approximately 7.4. The pH needs to be constant or you get acidemia or alkalemia, with both of which you don't want to get. Now, let's just say that I dumped in a lot of these hydrogen ions. Pause the video and think about it. As I've said, just because it has more terms doesn't mean that Le Chatelier's principle doesn't apply. So it's going to shift over to carbonic acid, but then it's also going to make more carbon dioxide and water. Because remember, it's only going to shift to this side if the reactants on this side go up. So the reaction going this side will take over. And then the hydrogen ion concentration will go back down to normal. But what if we added a base so that it uses up the hydrogen ions? This time though, it's going to shift toward the bicarbonate and hydrogen ion side. In other words, it's going to make this side equilibrium take over. Now I haven't mentioned it, but equilibrium expressions all have equations. If we go back to our ammonium bisulfite equation, we always put products by reactants. So our product would be the concentration of ammonia gas times the concentration of H2S gas divided by the concentration of ammonium bisulfide. Now, for example, if I put a 2 on all of them, we put this coefficient as an exponent, like this. So that was a short lesson about equilibrium equations in the mathematical world. So let's see a 3-way equation instead of the 2-way. Remember, this is 1, 2. Now, the lesson of equilibrium just got more complicated, right? Here, calcium oxide plus carbon dioxide plus H2O will become calcium carbonate plus water, or calcium hydroxide plus carbon dioxide gas. Here, what if I pour in a lot of carbon dioxide gas? Let's just attach it to a pump. So the carbon dioxide concentrations will go up. Because calcium carbonate side is the only one not involving CO2, it's going to shift towards the calcium carbonate and water. So, until it's back to equilibrium. But what if I just got rid of the carbon dioxide pump and then put in something else? Say, a vacuum cleaner. So, vacuum cleaner. Now, this vacuum cleaner will only suck out gases. Let's just say that. Now, pause the video and think about it in a little while. Well, then the carbon dioxide will become 0 because the vacuum cleaner sucked all of it in. Because it's 0, the calcium carbonate will have to dissociate to form more of calcium hydroxide or calcium oxide. Let's try something else. How about something more exotic? Say, I hired a plumber to get this faucet on, and then I drained all the water and carbon dioxide. No, let's just say I just drained all the water out. What do you think will happen? Well, because water levels reach 0, the only term without any water is calcium hydroxide. So, what it's going to happen is it's going to shift towards the calcium hydroxide this time. Like this. Equilibrium expressions are fun, aren't they? I got fun with it too. Here's our last expression. This time it's the opposite of endothermic reactions, called the exothermic reaction. This reaction emits heat instead of sucking some in. But the reaction here is reversible, so water plus heat can dissociate into hydrogen plus oxygen. Now, let's just condense some of our water into a liquid. Now what do we get? Well, because the equilibrium equation is different. Water as a liquid will only have a 1 here, so it wouldn't count in the equilibrium expression. Divided by the concentration of hydrogen squared times oxygen in gas. Let's go write our equilibrium expressions for the other two. Here, I have calcium carbonate solid, calcium oxide, and carbon dioxide. But, for some reason, solids are not allowed in the equilibrium equation. So, the only thing left will be carbon dioxide. So here, the equilibrium equation would just be carbon dioxide, the concentration of it. Here, it's just going to be ammonia times H2S. And thanks for watching the video on equilibrium expressions, equations, and Le Chatelier's principle. See you in our other episodes. Bye!